Okay, so I'm going to talk about a model for testing conditional local independence testing for dynamical systems, and in particular, model by event processes. Okay, so I apologize in advance. This is the only slide with data in my presentation. But the main motivation is to be able to learn the causal temporal atlas of diseases of a given population. So in Denmark, all the data related to the health of the population is centralized. And so we have theoretically access to the follow-ups of all the individuals of the Danish population. And there has been some works that were published already, for instance, in Nature. So this is a result of one of the papers from Hidalgo and his colleagues, where they kind of estimate a certain graph where all the nodes here are the specific diseases according to some references, and the edges here they can represent some kind of prevalence between two diseases. Okay. And the main motivation of this project is to be able to build such a graph, but under some causal framework. Okay, why so? Because there are some limitations of these methods. First, you see that the edges here are undirected, so there is no time relation between one disease to another. There can be some estimation bias for diseases of different prevalence, for instance. And if you look into the statistical methods that are used in order to output such an estimation of the graph, then you can see that they use some descriptive indicators to build the trajectories and the specific clusters here that you can see. Okay. And there are other results that you can interpretation that you can obtain from this type of graphs, but mainly there is no causal interpretation that you can draw from these results. Okay. So let's try to understand a bit more what is happening here. And first, let's try to formalize this mathematically. What is happening? Okay. So I ask you just if you can look at the first graph on the top left. Okay, so suppose that I'm looking at 4 diseases. Okay, and I have here the events that each of the disease occurs here, and on the right I have the random times that a particular disease will occur. Okay, so in within 0, 1, and the disease 1 will appear at time 1, and it will reappear, etc., until time tn. Before the end of the observational time. Okay, and based on these random occurrences, then I can define my counting process at a particular time t as the Dirac. In essence, I count how many occurrences have happened before my time t. All right, and this is for one coordinate, but of course you can index it for coordinates. Okay, and what is interesting is to be able to know if, for instance, the blue disease here has influenced or not the disease in green here. Okay, and how can I look at this? How can I answer this question? Well, first you can look at the intensity process, okay, that describes the probability that an event occurs in an infinitesimal interval of time given the past. So the intensity process is this function lambda indexed by time, and I want to it approximates the probability that there will be an event in my infinitesimal event time dt given the past, which is represented by this sigma algebra. It's just the information that I have until my time t. All right. And here you have on the left, again, you have the graphs of the intensity processes for each of the coordinates. And every time there is a jump that is large in a sense, then you see that there can be a corresponding event at that time. Okay, so this is kind of the idea. Okay, so once I have modeled the follow-ups of my individual using these tools, then the question that the problem that I would like to solve is to learn my underlying graph. Okay, and here thank you for I thank the previous speakers that introduced a large part of the literature. Here, of course, I suppose that I do not know the Oracle underlying graph, right? And why do we care about causality in this setting? We would like to know what happens if we intervene at a particular node, one of those, to quantify the effects of possible treatments for which we do not have observational data. Okay? And so the question that we ask in this project is how to learn if an edge exists with high probability in the causal framework. Okay? Please interrupt me if you have any question, of course. Okay, so a way of answering this question with high probability is to use conditional local independence testing, okay? And local is because we are looking at time-dependent data, and I can take my previous graph and generalize it a bit, where I don't have only 4 diseases, I have D diseases, and my outcome is modeled by the GF coordinate, my treatment is the H coordinate, and I have a set C among all the coordinates 1 to D that represented confounders that can be observed or not. And to be able to test whether there exists an edge or not in my graph, I want to test at a particular level alpha whether H has an effect on my outcome J given my confounder versus the alternative. All right, and you can see that here we will not have an edge, whereas here we will. Okay, and so the intuition is that the conditional local independence test, the infinitesimal local effect at the time t plus dt of the process of my treatment on my outcome, given the past knowledge inherited by the coordinates indexed by the set C, right? And I gathered three challenges, at least that are interested to us, but there is a list of other ones, of course. So first, it requires a model for the type of independence that we consider, okay? And there are some works by Shane Peters and some follow-ups as well, where they show that you cannot hope to have uniform power against any set of alternatives, okay? So you really need to rigorously define what type of independence you're looking at. You need a model for the processes that have good properties. What I mean by good properties is that typical examples of processes are not collapsible. And why do we care about this, and what does it mean? It means that when we look at a subset of information that is modeled by this set of coordinates C, then the model class that we obtain once we marginalize it is still in the same class of, belongs to the same class of models, okay? And the last point is that there is a lack of learning algorithms for known distribution of processes without the knowledge of Oracle graph. Okay, and I've listed here some existing algorithms in the time-independent framework, but I will not go through it because it has been discussed earlier. Okay, so let's focus on the first challenge. Okay, so in fact, we will not propose a new test for conditional local independence, but we rather will propose a model for an existing one that was proposed by Chris Gao, Peterson and Hansen 2 years ago. And it's based on the local covariance measure, where if I consider FC to be the sigma algebra generated by the C coordinates, it's just basically the information that I have from my coordinates over which I condition. And let's consider X to be a function of my treatment process. Then if I look at the expected value of my treatment given my information until t minus, which is the predictable projection of xt, and I consider the martingale given by the coordinate of the outcome, then we can build the local covariance measure test statistic that just looks at it's a kind of a correlation between the residual when I project X with respect to the information that I have and the martingale part of my outcome process. Okay, so just think about it as really a covariance between a functional of my treatment and a functional of my outcome when I specify with respect to the information that I have. All right. And some examples of test statistics are, for instance, that the one that depends on the endpoints. So when t equals to 1, otherwise you can look at the largest deviation of this measure over my observational time. Okay. And they prove some very nice guarantees under the null and under the alternative, and roughly under the null, then because you end up with some kind of martingale process, then you can prove some explicit asymptotic null distribution, and also you prove that it's uniformly asymptotic of level alpha. And under the alternative, then they prove that the test has power uniformly against local alternative as soon as as soon as the subnorm of the test statistic decays at a good rate with the sample size. Okay, but you see that in order to compute this test statistic here, the expectation of this covariance measure, then you need a model for the predictable projection pi and the martingale counterpart of my outcome process, right? And we go to the second challenge that I've listed here. We want to find a good model class that are not collapsible. Okay. And as a first case, then let's see some typical examples of point processes. So, so first you can think about point processes where just the intensity function is deterministic and has some nice regularity properties. Or you can go a bit further and look at multivariate Hawkes processes where basically the intensity process of a given coordinate j, you can forget about the psi here, but it's just the sum of some interaction between the other coordinates I here, and depending on the sign of H, then you can say that the process is self-exciting or self-inhibiting, yes, and roughly, so it was this class of processes was introduced for epidemic type aftershock sequences of earthquakes initially, and it's very used as well in financial type of data for portfolio dynamics modeling and analysis. Okay, so we can essentially, apart from reminding some of the typical examples of point processes, you see that the intensity process kind of characterizes the stochastic behavior of your process. Okay? Okay, and in the literature, so so once you have chosen your class of for your intensity process, then you can ask the question: how can I estimate the parameters of my intensity process, right? Historically, there is you can try to maximize likelihood-based risk. And there has been many, even very recently, very interesting improvements, especially for multivariate Hawkes processes, when you impose structural assumptions on the underlying process, and some more theoretic treatment. You can see Hansen and Deborah also. With Judith Rousseau and Vincent Loira. And more algorithmic treatments, you can see those, and apply to EEG data, for instance. And another perspective is to try to minimize a least squares penalized risk, okay? Where you will penalize this least squares risk with some penalty that depends again on the structural assumptions that you want to do, that you're able to make on the underlying mechanism. And here are some references, and we gather everything in a book chapter that will be published soon. But unfortunately, there are some main limitations on these methods. Okay, so they are tailored for some parametric models for intensities, such as Hawkes processes or other that come from survival analysis, but they are subject to model misspecification because they are non-collapsible. And if not, then you can see that, for instance, the Hawkes process, you have this sum of interaction between all the nodes with the one that you're interested in. So you kind of look at the first order interaction. Usually those methods are only based on one observed process that can be in a very long time interval. And when you think about the initial motivation, we have a data set for a given population. So we have to take into our consideration the number of individuals that we observe, especially as we are in a very high-dimensional setting, right? We have a huge number of possible diseases. And the last point that I raise here is the fact that these methods are especially the ones based on the likelihood maximization, are highly computationally costly due to the memory characteristic of temporal point processes. Okay, although you can reduce if you have some structural assumption. If you make some structural assumptions, okay? And so our approach is to propose a generic non-parametric model based on a linear decomposition using an information basis processes that take the form of nonlinear stochastic terms with memory. And I will explain this in a minute. And we propose to estimate the optimal parameters of our decomposition using a penalized least square objective function, namely the lasso, for which we derive non-asymptotic control of the estimation and the prediction excess risk, where we have the data-driven concentration inequalities. And lastly, we propose a procedure, practical procedure, but we don't have numerical results yet. Okay, so let's jump into the approximation model that we propose. So here's just to remind you the framework. Well, I'm not gonna spend too much time on it, but I just want to remind you that we look, for simplicity, we look at a counting process here that is of dimension D, okay? The coordinate of interest is the gth, and C is the subset of coordinates that would represent the confounding in the causal framework. The goal here is to be able to approximate any real valued process Y based on a subset of information encoding by C that we will define by V, okay? So we observe, yes, so we want to exactly to model the Y, but only based on the information that I have thanks to the coordinates, the C coordinates, okay? And we show a generic approximation model for this V process, all right? So what do we mean by approximation model? Then is similar to dictionary learning, right? So we have our stochastic information basis Z here that is composed of some square integrable processes, and K can be a set of multi-indices based on C. And so the idea is to approximate my process V using a parameter theta as this linear combination with theta and my basis processes Z, right? Sorry. And if I go back to the initial examples, then you can take Z1, for instance, or to be just a deterministic function and to model the Poisson process. If now we go a bit further, then you can take K to be the set of indices, so to be exactly C, and then you just need to consider those information basis processes. And then if I want to go a bit further again, I can go to the second order decomposition, right? So I will have the terms that correspond to the first order. So let's say that we have up to K here is K1 and K2. So I have the two processes related to the first order, and then I have Z of K1 and K2 that will be just the product of the two. So I avoid some additional technicalities, but here is just the idea of how we go a step further at each time. And we can end up with the general Voltaire expansion, where you just need to, you have all the terms of lower order, and then the term of largest order K will be the product of the size of these EPFL K of all these linear filters, right? Where all these functions G and H are deterministic and are some kind of regular enough. All right. And so now that I have chosen my specific decomposition, I have fixed my stochastic information basis, I can ask how to learn the optimal theta. Okay, and we propose to do so by minimizing the least squares contrast function on the observational time 0, 1, where it's just the L2 norm between my model V of theta and the true process V that I do not observe. Okay, and what it corresponds to, I just integrate on 0, 1 the square difference between Vt and V. All right. So in essence, I can rewrite this, and I want to estimate my oracle parameter that minimizes, and you see it takes, we recover the classical formulation of a least squares contrast function, right? Where we make appear the Gram matrix that depends only on the process composing the information basis, and V is the vector where you look at the inner product between the basis process and the unobserved true V process. Okay, but there are at least two problems. So we only assume the information basis processes to be square integrable and not uniformly bounded on any compact 0T. And also here the true process Vt is unknown, and we only suppose that we have observed a sample, an ID sample of the Yi's, and that's an ID sample of the information basis, right? And the goal is to be able to prove non-asymptotic properties in N, because we have fixed the time horizon t equal to 1 for simplicity, and generalization performance of theta hat. Okay, so we take an empirical risk minimization perspective to answer to those questions. Right? And so, because we are in a very high dimensional setting, we can look at the lasso equivalent problem, and we want to learn this theta hat here based on our data sets. So we just take the empirical averages. This is why you see a hat and subscript n, plus the weighted L1 norm here of theta, and where we need to rescale those theta by omega n in order to rescale all the longitudinal data that we have. Okay. And we consider, for the theoretical perspective, we consider the probabilistic events E1, where I suppose that my subnorm between the unobserved estimator of my V vector and the observed one can be upper bounded by the weights that I use in my risk. And the second E2, where it's kind of related to the invertibility of the grammar matrix in a certain subspace. Okay, we will talk about this soon. Okay, yes, and in particular here, so we want the random grammar matrix to be kind of have some invertible conditions, properties on the cone here C of S. That is based on the support of theta prime. So S of theta prime is the support of theta prime, and CS is just the related cone, where we suppose that the coordinates in the complementary of the support are smaller than those in the support of interest. Okay, so this is related in the literature as a restricted eigenvalue property. All right, so the first result that we obtain, and that is kind of already interesting, is that here, if you look on the left, so if you consider first the empirical solution theta hat of the lasso problem, then on the events, if we suppose that both events are fulfilled, then you can upper bound the estimation error here on the left-hand side of the inequality by a sum of some terms, where what is important here is this term, right? So here you have the empirical approximation error, which means that how good my model is to approximate my unknown process V. Okay, and then you have some data-driven terms. Okay, so what we see that everything is data-driven except the approximation error, and this approximation error is inherent to the choice of the stochastic information basis that we have. And we can see that if the weights Wn are of order at least as that of the approximation error, so what I mean is that if this is as comparable to this term, then we can hope to achieve the rates of the approximation error. Okay? But you see, there is a kind of a limitation to this first result, because we pay the price of this 1 plus A. okay? And A can be actually very large, right? So we would like to make this A tend to 0 in order to hope to do as good as we could do in the upper bound of the inequality, okay? And we can achieve this, but it comes at a price, and the price is that we need to solve the problem according to the primal dual witness construction, and roughly it would require some knowledge about the support of the oracle parameter. But then if we have this, then we get rid, so here you see we just have a constant equal to 1. So we can achieve at best the rate of the approximation error if we have this additional information, okay? And so I just want to stress that both results hold true for general stochastic basis and not necessarily only for the Volterra expansion, okay? So let's now discuss a bit about those events, that the assumption that we assume in order for the result to hold true, and if they are reasonable or not. Okay, so if we look at the event E1, so we want to control the worst empirical approximation bias between the unobservable estimator V bar and V hat, okay? So if the process V is the intensity process of the GS coordinate of a counting process, then we can choose the weights of order square root of log of the size of my dictionary divided by n to achieve sharp upper bound. And we can explicitly have the probability of the event E1, okay? And I've added some information about how to obtain those results. And now if we look at the event E2, it's a bit more difficult because, we place so first, why is it important? So as we place ourselves in possibly very high dimensional setting where the size of my dictionary is way larger than the sample size, then we need this extension of the restricted eigenvalue property, ensuring that along the important axis of the oracle parameter, then the empirical graph matrix is invertible, and its control of which the smaller eigenvalue is kind of controlled by this parameter kappa. Okay, and in fact, this assumption is quite difficult to theoretically check for a generic stochastic basis information, and we would like to numerically estimate it. And the intuition is that if I can choose a kernel, so remember this function g and h, if I can choose such functions to obtain that we have kind of independence, and it's related to when we have time independency, orthogonality of the columns, then we can have a better understanding of this event E2. Okay. Okay, so let's go back to our initial problem, which was testing conditional local independence testing, where I would like to test whether my treatment has an effect on the outcome, on the disease, given the confounders. Okay. So I want to check whether there exists an edge between H and J here. All right. So I want to use this local covariance measure, right? And you remember we needed a model for the intensity process of the outcome process coordinate J, and we wanted a model for the predictable projection of related to the treatment that I give. All right, so we can suppose that they are modeled according to what I proposed earlier, and the goal is to be able to learn these parameters beta and eta, right, where I use similar notations. And if I go back to the lasso contrast function, then we need to estimate for any index k and k prime this beta hat and eta hat, where those linear terms are approximated by what I can observe. And for beta, so it's related to the counting process N, and for eta, it's related to the treatment process X. All right. And so a sketch of the practical procedure would be that if I have fixed all my coordinates and I have chosen a significance level alpha, and I have my RID observations of the counting processes related to really the data, the health database from the Danish population, for instance. And if I choose those classes of kernels, G and H, then what we propose is to split the data set in two. So on the first D1, we propose to estimate those parameters beta hat and eta hat, minimizing the lasso contrast function. And then on the second data set, then you can compute the LCM measure and then choose a test statistic that is based on the LCM of your choice. Okay. And once you have obtained the numerical value of this test, then you can reject or not the existence of an edge in your graph. Okay, so to conclude, and I think yes, what we did is that we proposed a non-parametric model for non-point processes using linear decomposition on a stochastic information basis, and for example, we pointed at the Volterra expansion. We have obtained optimal empirical parameters that minimize the lasso objective risk with a weighted penalty term. Okay, and we have proved some non-asymptotic exact or not oracle bounds at rate that is similar to those that we are used to in ERM literature, that is of order square root of the kind of the complexity of the class divided by n. And I've presented you those related to the estimation error of the minimizer theta hat, and I skipped the prediction error in the interest of time. And we are interested in the future, so we hope to submit it soon. And the next steps would be to provide a fully data-driven bound for the prediction error, and to provide also a practical algorithm for really learning the whole for causal discovery in this very high-dimensional setting that we have. Thank you. Thank you.
Thank you very much. Are there any questions? Okay, so let me ask a question. So what you explained, you started with this complicated graph that was not directed, but then the methods that you proposed are supposed to give the direction on the graph,
Yes.
right?
Yes.
And so did you work this out, and then are there supposed to be clinical experiments to somehow determine if the method works in some way?
So thank you for your question. So it's actually a very difficult question, and there are ways of choosing the direction of the arrow, and those are works that have been developed in those kind of graphs in the local independence graphs by Søren Mogensen and Niels Hansen as well. And yes, I invite you to look at all the methods there, because it depends on whether you suppose that the confounding is observed or not. And then the second question about the clinical trials, I'm not aware, but I can imagine that it's something, for instance, in Novo, or where you have longitudinal data and you would like to learn the underlying causal graph, where you don't, because usually the methods are based on knowledge of an oracle graph that is usually, if my understanding is correct, is based on knowledge of experts. So they go and ask the doctors to be able to draw the graph of the underlying phenomenon, and then so that you have some kind of oracle in a sense. But even in that case, there are some works by, for instance, the biostat team in the University of Copenhagen that look at how to deal with this expert knowledge to be able to build the oracle graph.
Okay.
I don't know if there's...
Yeah, makes sense. Makes sense. Yeah, okay. So last question, because we have to move on to the panel.
Oh, gee, well, if you're short of time, I don't.
It's okay. We'll just go on.
I just had a question about the very start of the talk. The schematic diagram you drew of the diseases, and I just felt like I could understand the form here. Yeah, the next one.
Ah, sorry.
This one, yeah. I felt like I could understand intuitively the red intensity plot and the turquoise one, but then I was thinking, how that sort of increase when you see an event, but I couldn't quite understand the green and the purple ones.
Oh, right. So I think it's okay. So it's a very schematic graph, but the idea is that here you have it. So we draw this function, right? And the idea is that if this probability is significant, then you will have an event on the top graph, right? And here the idea is that some of the jumps here, if you look at one coordinate, it can imply a jump in another coordinate. Okay. Yes, because of the sort of dependence. Yes, exactly, because given another IC. Because mathematically it's really this. So forget about the psi and the mu. So for a given coordinate, then you sum all the linear filters over all the coordinates, right? Yes.
Okay. All right.
I have a question.
Is it okay?
Yes, sure.
Yes. Right, yeah, we have to move on to the panel because we have to also prepare the room for that. So I encourage you to ask the question later.
Okay.
But let's speak again and.